Okay, so welcome back, everybody. Before I kind of touch on the last bit of material that I wanted to talk about, I wanted to consider the following questions. This is a famous question asked originally in the 60s, which is, can one hear the shape of a drum? So this is originally asked by Cack in a famous article in 1966. So what is actually being asked here? Well, what's being asked is whether you can like definitively say something about the shape of like the drum head. So we'll say that just consider it even in 2D, right? So consider in 2D um, the problem of a two-dimensional drum head, right, as we talked about yesterday, like in the example of like a vibrating circular drum head. So now imagine that I have a two-dimensional region. This looks like I said boundary of D, but this is 2D. So imagine that I have a two-dimensional region D in the plane that looks like this. Right, so here's my two-dimensional region. You can think about this as being the shape of like a membrane that I have stretched over the drum. This is kind of if I'm looking straight down at the drum, this is an oddly shaped drum, right? So this is the top of the drum. This is the membrane stretched over the drum. And the question is, if I have some other region like this, say D prime, um, can I definitely differentiate between these two drums, hearing their sound, right? So do these two different regions, right, definitely produce a different sound? And in a way, right, the idea is, can I, just from the overtones alone, okay, which we'll see are actually, the way we can categorize that is think of these as like eigenfrequencies, which are these frequencies, the associated with these eigenvalues that we've talked about this entire time for these sorts of problems. The question is, just from that list, can I tell what shape the drum is, right? So another way of saying this is it possible, right, that I could have two distinct regions, say D and D prime, that produce the exact same list of eigenfrequencies here, or the exact same list of these associated eigenvalues. And this was an open question. So in the original article, Cack admits like he doesn't actually know what the answer to that question is, and this wouldn't actually be solved even in the 2D case, right? This remained open. So even in 2D case, this remained open until 1992. Okay. Um, and so in 1992, the answer was no. So in 1992, this was answered in the negative by Gordon, Webb, and Wolpert. Uh, and they constructed explicit examples of two distinctly shaped drum heads that produce the same eigenvalues. and we'll call them eigenfrequencies. If you want to see those examples, there's a good Wikipedia article that lists all of the relevant references there, so you can look at Wikipedia. I'll post it in the chat right now. So here, so I just posted it in the chat. You can have a look at that. It's a really nice kind of treatment of this. It gives you an explicit example showing that no, in fact, just hearing the overtones is not enough to determine this. If you want to see how this relates to these questions, right? So we just talked about a vibrating drum head yesterday for the special case of circular drum head, and we got these Bessel functions, right? These Bessel functions, as I said, were eigenfunctions for the Laplacian, right? On the domain in question. And so, where does the analysis we've done come into this? So where it comes into this is the following. Well, the actual equation we're considering here, if we're talking about the eigenproblem for the Laplacian, right? So eigenvalues, maybe I'll do it on another page so that I'm not cramped down here in the corner. So when I talk about eigenvalues and eigenfunctions of the Laplacian, on some region D, what is the associated problem? Right? The associated problem is, so remember, what was our eigenvalue problem for our operator that we've used for this entire separation of variables? Bit, let's do this on a separate sheet. Maybe I'll do it on the back here. So, you know, our problem looked like this. And then we had boundary conditions, right? So like the Dirichlet problem. So this was our Dirichlet eigenvalue problem. So it was this thing on region in question. It was a 1D region, of course. And x equals 0 on the boundary, which for a 1D region was just 2 endpoints, right? This is what this eigenproblem looked like. Well, what about for the Laplacian? It is going to look like minus Laplacian u equals lambda u on D. And if it's the Dirichlet problem, u equals 0 on the boundary. Right? Okay. So here, you know, this is the associated Dirichlet eigenvalue problem for the Laplacian, or minus the Laplacian, as we write typically. And so, how does this translate into this question of hearing the shape of a drum? We call two domains, D1 and D2, isospectral. Okay, if they have the same eigenvalues. Another phrase for isospectral is homophonic, because the implication here is that if they have the same eigenvalues, they produce the same overtones, if you think of them as vibrating drum. Okay. And so the question of can one hear the shape of a drum? This question can be reformulated slightly, right? So this can be reformulated to ask whether or not these eigenvalues determine the domain, right? So, i.e., can I determine the domain D if I know the eigenvalues? Another way of saying that is it possible for two domains to be isospectral while being different? i.e., do there exist different, that is distinct, right, D1 and D2 that are isospectral? And the answer to this question, if there exists two distinct domains that are isospectral that have the same eigenvalues, the answer is yes. And for that reason, we can't hear the shape of a drum in that sense. The list of overtones, those eigenfrequencies, that's not enough to determine uniquely the shape of the drum. Okay, and so the answer was a negative one. There are various reformulations of this, either in higher dimensions or under certain assumptions. So it's been shown that under certain assumptions on the boundary of this region, the answer to this can be yes, right? So the answer to this can be yes with certain additional restrictions, but the unrestricted problem, the answer is no. Okay, and as I said, if you want to see like a whole list of domains like this, you should have a look at that article that I linked. So you might notice, like, this is an example of what you could call spectral analysis. So spectral analysis, spectral geometry, and of course we had the spectral theorem. Right, that we talked about, and we had the more general spectral theorem for Hilbert spaces that we also mentioned. What does this word spectral mean? This is from an older terminology for eigenvalues to begin with. The list of eigenvalues for a quantity, either an operator in this case, or going all the way back to the matrix, was called its spectrum. Okay, and in general, when you see the word spectrum popping up, or spectral popping up in a mathematical context, that means that it's the main object of study in some way is like an eigenvalue problem. Okay, so this, of course, is extremely, there's so many different fields where this pops up that I can't possibly list them all, but this is a very important thing. Okay, so that was one kind of problem that's related to some of the stuff that we've been doing that I wanted to address. Now, what I wanted to do is to continue sort of in the same spirit of what we were doing in yesterday's lecture, to consider, what if I wish to solve, say, the 3D. We've done the 2D diffusion equation and we did the 2D wave equation. What if I wish to solve the 3D diffusion equation, or 3D wave equation? So first, let us consider, well, if I'm thinking 3D wave equation, of course, that's u sub t equals Laplacian of u. We'll say I pick my constant to be 1 here, or u sub tt is equal to, here, let's write that as alpha, c squared Laplacian of u, where now this Laplacian is the 3D Laplacian, right? So it probably isn't too surprising to you that in the same way that this worked in the 2D case, I'm going to investigate like the 3D Laplacian and see if I can solve like 3D Laplace's equation, see if that leads me down the correct path here to being able to solve the 3D diffusion or wave equation. And so the question is, first, let us consider the 3D Laplace's equation. Which, of course, is Laplacian of u equals 0. Or in the 3D case, this would be u sub xx plus u sub yy plus u sub zz is equal to 0. Okay. Now, first, for a variety of reasons, for instance, if we wanted to eventually talk about these things maybe in a 3D ball, then it wouldn't be shocking to you that spherical coordinates may come into play. And indeed, spherical coordinates were a thing that was something that you used quite a bit in Calc 3 whenever you were doing, well, pretty much any sort of situation you're in where you found yourself dealing with spheres or 3D balls or parts of those things. You wanted to talk about spherical coordinates. Even cones, right, were nicely described in terms of spherical coordinates. So spherical coordinates was something that came up quite frequently in Calc 3. And so first we consider spherical coordinates. So if I have spherical coordinates rho phi theta, then I can write my Laplacian in terms of spherical coordinates as follows. So my Laplacian in terms of spherical coordinates can be written as, again, this is just chain rule. Okay, so by the chain rule, this is 1 over r squared times the r partial of r squared times the r partial plus 1 over r squared sine phi times the phi partial of sine phi times the phi partial plus 1 over r squared sine squared phi times the double theta partial. This is the Laplacian in spherical coordinates. Now immediately you might be thinking, oh, this looks like a huge mistake to write it like this, right? Isn't that so much nicer, right? Why would I write it like this? Well, if we are going to be, say, solving the 3D diffusion or wave equation in 3D ball, it still makes sense that ultimately describing this in terms of spherical coordinates may work out to our advantage here, may be simpler, or at least maybe conceptually better for some reason. So in the exact same way that I've been doing the whole time here, I want to apply separation of variables. Now, separation of variables tells me what? I want to seek u of rho phi theta. That is, so the textbook, instead of using rho here, uses r. So that maybe I should, if I wrote this, maybe I should write this as r instead of rho. Let's do that. So instead of rho here, let's write r. I actually copied it here as using r, but here. There we go. Okay. So r phi theta, that's fine. If we seek a solution here that's totally separated in the sense that this is r of r times phi of phi times, oh, no, not phi of theta, phi of phi, times theta of theta. This is my ultimate goal, but for a reason that we'll see later, for now, seek solutions that look like this. You have r phi theta is r of r times a function we'll call y of phi theta. Now, why wouldn't we separate this completely? So what we end up solving, we are going to separate it completely, but the reason for writing it like this for now is that it turns out that these y's have a very nice form, a ton of very nice properties, and ultimately are going to be something called spherical harmonics that have applications all over the place. And so we have a good reason for writing it like this to emphasize this quantity. Okay, but let's write it like this for now, do separation of variables, and then we will fully separate this eventually in solving this anyway. So let's plug this into Laplace's equation using the Laplacian here in terms of spherical coordinates. So quickly through this, you can check the computations later. If we plug this in, then Laplacian of u is going to be equal to y over r squared times the derivative with respect to r of r squared r prime plus r over r squared sine phi times the phi partial of sine phi times the phi partial of y plus r over r squared sine squared phi times the double theta partial of y is equal to 0. So this is the giant mess that I get out of that. Now, what I want to do, since this is equal to 0, I want to take this ODE and do the algebra I need to in order to put everything involving phi and theta on one side and everything just involving r on the other. So if I've done that correctly, what I get ultimately, so like I said, moving this term over, or moving both of these terms over, dividing through by r here, dividing through by y here, I get 1 over r ddr of r squared r prime, and this is equal to minus 1 over y sine phi times the phi partial of sine phi times the phi partial of y minus 1 over y sine squared phi times the double theta partial of y. So these are equal to each other. Okay, and of course this has to be true for all r, phi, and theta, which means that since this is a function of r, and this is a function of phi and theta, these have to equal some constant, right? Call that constant lambda. So these must be identically equal to a constant we'll call lambda, as usual. So this is going to give us our first eigenvalue problem by considering the easier side here. So this leads to the eigenvalue problem d 1 over r ddr of r squared r prime is equal to lambda, which gives us the eigenvalue problem by multiplying both sides by r. This is ddr of r squared r prime equals lambda r. So this is the eigenvalue problem for r. And it turns out if you expand this thing, you'll see that this is another example of a Cauchy-Euler equation. Right? So this is a Cauchy-Euler equation. And from last time, what was the advice for a Cauchy-Euler equation? You can guess or just try a solution that is r to the L for some L positive, and the lambdas resulting here are of the form L plus 1. So here's our eigenfunctions and eigenvalues. Right? Parameterized here by L instead of N. Right? We're using L here. Okay. All right. Now, why are we able to say that L has to definitely be positive, can't be negative? This is going to come from, again, considering that we want this thing to be smooth everywhere, even at the origin. And if this is r to the minus L, then this quantity showing up in our separated solution here would lead to something that's not smooth at the origin, right? But we want it to be smooth at the origin, so we know these have to be positive here. Okay, and so now this is the eigenvalue problem I got from the left-hand side. For the right-hand side, if that is equal to lambda, then moving everything over by multiplying by a sine phi, what do I get? So the other side, I get that. So here what I want to do is, so I have this thing is equal to lambda, right? So both of these equations are equal to lambda. Maybe I'll just write equals lambda here. So you can see, so if I multiply through by sine squared, that clears denominators here, and I get a minus sine phi over y times this thing minus 1 over y times y sub theta theta. And so what I get here, if I move my minus signs over to the lambda, this would be sine phi over y times the phi partial of sine phi times the phi partial of y, plus 1 over y times the theta partial of y is equal to minus lambda sine squared phi. So that is the equation I get. Okay. All right. Now I want to do separation of variables again, separating the variables in y. Remember the way I wrote this y, I hadn't separated phi and theta here, right? Which is why I keep having to still write these partial derivatives instead of writing them as full derivatives. And so now I want to separate the y here, right? So separation of variables on the y. So seek, let me do it like this. So then seek y phi theta of the form, we'll call it phi of phi theta of theta. So phi of phi theta of theta. Okay. So then what does this equation turn into for this? Well, this is going to be sine phi over phi times the phi partial of sine phi times phi prime. Right here, let's rewrite these so that I don't get really confused here. Plus theta prime over theta, both of these are big theta, okay, is equal to minus lambda sine squared phi. And then doing some algebra here to put all of the phi terms on one side and all the theta terms on the other side, what I get is sine phi over big phi times the derivative with respect to phi of sine phi big phi prime plus lambda sine squared phi is equal to minus big theta double prime over big theta. And so, why did I reorganize it like this? So that on the left-hand side I have nothing but phi, and on the right-hand side I have nothing but theta. Okay. So by this same reasoning, since this has to be true for all phi and theta, these both have to be identically equal to some constant. We'll call that mu. Okay. And so I get two more eigenvalue problems with implicit boundary conditions imposed that are periodic, right? So this leads to two eigenvalue problems with implicit periodic boundary conditions. Okay, so what are these things, right? So because, of course, how this is defined, these are 2 pi periodic for both of these, and I have the eigenvalue problems so let's do this one first since it's simpler. So minus big theta prime over big theta is equal to mu leads to big theta double prime plus mu theta is equal to 0. Hey, our favorite eigenvalue problem. All right. So that is this is the eigenvalue problem I get for theta, which in the usual way, this is for periodic boundary conditions for theta. So this leads to eigenvalues. Mu is equal to m squared for m some positive integer. So m's 1, 2, 3, and so on. Okay, and how many solutions, how many eigenfunctions do I get? Well, I get countably infinitely many, as usual. Of course, these are periodic boundary conditions for this eigenvalue problem, so I get the full Fourier series. But I'm going to write that using complex notation here. You don't have to do it this way, right? So remember, complex notation, like writing it as e to the I m theta, this is a nice way of organizing this, but you don't have to. You could write it as sines and cosines like we normally do, because the actual values of these things are real, even though an I is showing up in the complex version of it. All this is for historic reasons, and also it's just more convenient to write it this way in the final form. And so my eigenfunctions, or theta of theta, is given by e to the plus minus I m theta. Again, don't be too scared that we've used the complex form of this. Note, this is just the full Fourier series. Note, these are just the eigenfunctions corresponding to the full Fourier series. remember, the thing that's kind of annoying about having the full Fourier series is that rather than getting a single eigenfunction for every integer, you get two, right? You get two linearly independent ones, sine and cosine, right? But this is just a nice, convenient way of writing it. Okay, so this is just the full Fourier series here. Now we have both a mu and a lambda showing up for the other eigenvalue problem, but we've previously found that since the original eigenvalue problem for R was a Cauchy-Euler equation, we found those eigenvalues, right? Those eigenvalues were L plus 1, right? Where our eigenfunctions are this R to the L. Okay. And so, the last eigenvalue problem where does it come from? Well, I have to take this left-hand side here and set that equal to mu, right? So this is equal to mu, and I consider this thing. So it's going to involve both a lambda and a mu, but we just found out what mu is, and we know what lambda is. So we know both of these things, and we can solve this eigenvalue problem. Okay, so how are we going to rewrite this? So rewriting this left-hand side equation with lambda and mu, what I get is this becomes d phi of sine of phi times big phi prime plus L times L plus 1, that's lambda, times sine of phi times big phi is equal to mu, which is m squared, times phi, or big phi, over sine of phi. Okay, changing variables to make this a little bit nicer. If I do the change of variables, x equals cosine phi, right, where x is between -1 and 1, then what I get here is that d phi can be written in terms of d dx as minus sine phi d dx. And so using this change of variables here, I can change this equation into the following. So my ODE becomes the following. So this becomes d dx of 1 minus x squared times d dx of big phi plus L times L plus 1 minus m squared over 1 minus x squared times big phi equals 0. Now, you might look at that and say, how does that help me? Right? This looks even worse than the thing that I started with. But this ODE has a special name because its solutions have special properties. This ODE is called the general Legendre equation. Okay, this is likely not an ODE you talked about at all in your Math 246 class, but nevertheless is an important type of ODE. Now, we've done this change of variables for x between -1 and 1, and it might not be that shocking to you to look and see that, oh, actually, if x is equal to 1 or -1, there's singularities in this ODE. Okay, so yes, that's true. That's the case. But actually, we can get the existence of solutions to these for integer values of L if L is bigger than or equal to m. So we have solutions for integer values of L, if L is bigger than M, or the absolute value of M. So remember, M was, remember how we wrote M previously for our other eigenvalues. Okay. And so, what do I have here? I have a set of eigenvalues that are M squared, another set of eigenvalues that are L times L plus 1, right? And those are eigenvalues so long as L is greater than or equal to M. Okay. So then what are these solutions called? The solutions to the general Legendre equation are called Legendre polynomials. Which can be a little bit confusing. So sometimes we can call them, and these are, maybe I should here, actually. Let me try to eliminate some confusion here, because we're going to use these terms in a bit together. So these are called the associated Legendre polynomials. So these are called the associated Legendre polynomials, or associated Legendre functions, since it will turn out that for some values of M, these things won't be polynomials, since for some M, they won't be polynomials. Okay. We write these solutions as the following. So we write these as P, so subscript L, superscript M of X, and by our previous change of variables, if X is cosine phi, for us, i.e., our eigenfunctions here, our eigenfunctions are given as big phi of phi, which is this associated Legendre function P sub L superscript M of cosine of phi. And so let's put all of this together. All right. I was seeking solution was separated r times phi times theta. Using separation of variables, we found that the eigenfunctions and eigenvalues for r, the eigenvalues were L times L plus 1. The eigenfunctions were r to the L. The eigenfunctions for theta were our full Fourier series eigenfunctions, the sines and cosines, which we wrote using e to the plus minus I m theta. And then lastly, we have these eigenfunctions that look like this, these Legendre functions or Legendre polynomials of cosine phi. And so our separated solutions look like this. Our u sub L m of r phi theta. These are r to the L e to the plus minus I m theta times the associated Legendre function P sub L sup m cosine phi. And so our solution, right? Now you could say, can we do this next step that I'm about to do? Well, only if these eigenfunctions we've gotten at each step satisfy certain orthogonality properties and span reasonable functions. But actually, let's look at what these are. So these were, I had r to the L here, I had sines and cosines here, and then lastly, I have these Legendre polynomials. So these are the mysterious ones, right? It turns out that these satisfy all the relations that we want, but to see that, we need to talk about them a little bit more. So we'll do that in a bit, okay, in just a few minutes. And so this means that the solution I seek, u of r phi theta, is the sum from L equals, say, 0 to infinity. Sum I can sum over plus n minus m's if I'm using this. If I had used sines and cosines here, right, if I wrote this as linear combinations of sines and cosines, then I would only need to sum over the non-negative m's. But I'm going to write this as a sum from m equals minus L to L, right? Why am I doing this, right? Why is this not an infinite sum? Well, remember, the way that this worked was that we had solutions for integer values of L where L is greater than or equal to the absolute value of M, right? And so that's why this M only needs to be summed from minus L to L. Okay. Of some coefficients, A sub L M R to the L E to the I M theta, P sub L sup absolute value of M cosine phi. Okay. Where these A's are coefficients suitably chosen to accommodate the boundary conditions. Where the coefficients A sub L sup M are chosen to accommodate the boundary conditions to our original problem. Now you have a question of whether or not you can suitably choose those coefficients. This is where the property of these Legendre polynomials being orthogonal, spanning reasonable functions, and blah, 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 comes into play. Okay, so that's what we have to know. All right, and so let's investigate these Legendre functions more in detail. So let's look more closely at these Legendre polynomials, or these Legendre functions. And so let's go back to our general Legendre equation. Here it is. And let's do this in cases, right? So let's do the case that m equals 0 separately, and then we'll do the case that m is not equal to 0, and show how these things are related. We're not actually going to prove these solution formulas. I'm just going to state them. Okay, so let's do case 1. M is equal to 0. So in the general Legendre equation, if m is equal to 0, this term goes away, and so I get d dx 1 minus x squared ddx of phi plus L times L plus 1 of phi is equal to 0. Okay, and so this becomes, so the general Legendre equation becomes just the Legendre equation in this case. And let's write it out. So if m is equal to 0, this becomes d dx of 1 minus x squared d dx of p we'll call it, since the solutions we're seeking, we labeled them P, plus n times n plus 1 P is equal to 0. This is what's called the Legendre equation. Okay. So after normalizing for a constant, the solutions to this ODE are just known as Legendre polynomials. So the solutions to this ODE are called Legendre polynomials. So note this is no longer associated Legendre polynomials. These are just Legendre polynomials. And we label them P sub n of x. They are given. These are actually polynomials, so there's no confusion calling them polynomials. So these Legendre polynomials P sub n of x are given by what's called Rodriguez's formula. So these are given by what's called Rodriguez's formula. Which states that these Legendre polynomials P sub n of x are 1 over 2 to the n times n factorial times the nth derivative with respect to x of x squared minus 1 to the n. So I'm not going to verify that that's the case. But if you want to get Legendre polynomials of any order, right, of any order n, you can just expand this formula. So it turns out that already this is an orthogonal family, and this also forms a basis for L2 from minus 1 to 1. So some facts about these Legendre polynomials. Okay, so one, if we call the family of Legendre polynomials P sub n of x, if n is in the natural numbers here, so this is an orthogonal family. What do I mean by that? I mean that if I integrate this from, say, minus 1 to 1, P sub n of x times P sub n prime of x, where n and n prime are distinct, dx, then I get 0, right? If n prime is not equal to n. Okay. Also, these are a basis for L2. On minus 1 to 1. i.e., if f is a function in L2, so if f is a square integrable function on minus 1 to 1, then there exist real numbers a sub n such that f of x can be written as this infinite linear combination of Legendre polynomials. So I'm not going to prove that, but that is a statement. So this gives us the property of the Legendre polynomials we like. The textbook calls this being a complete basis for L2. So these are exactly what we seek in our eigenfunctions, right? We're very, very happy to see these sorts of properties. Okay. Now, so that's in the case m is equal to 0. Now, what about the second case? So case 2, m is not equal to 0. So let's revisit our general Legendre equation. If m is not equal to 0, this is just the completely general case here. And now these associated Legendre polynomials, we're not going to prove that this is the case, but we can actually compute these in terms of the Legendre polynomials that we just wrote out. So, so the solutions are the associated Legendre polynomials, which we call P sub L sup m of x. Okay, they're only polynomials for even n, or even m, sorry, only polynomials for even m. But we'll call them polynomials in general just to do it. You could be a little bit more precise here and just call them associated Legendre functions. These can be computed from just regular old Legendre polynomials. Via the following formula. Again, I'm not going to prove this. So P sub L sup m of x is minus 1 to the m. Whether or not this is included in the definition of these things is actually kind of up to you. In the literature, a lot of times in quantum mechanics, it's going to be included here. I'll say a bit about that again in a second, but I'm just going to include it here. So this is minus 1 to the m times 1 minus x squared to the m over 2 times the mth derivative with respect to x of the Legendre polynomial of order L. Okay. So note really quickly, you may see these defined elsewhere, and this minus 1 to the m might not be there. The minus 1 to the m is referred to as the Condon-Shortley phase. And it may not be present in other, so it may not be present in other definitions of this, depending on where you're getting it from. And the reason why is this minus 1 to the m term, this doesn't actually impact the orthogonality of these things at all. This term can be moved to the other term in the product if you like, so it doesn't have to be here, but we're putting it here. It doesn't actually change the computations involved here. But yes, we can. So here's these associated Legendre polynomials, or associated Legendre functions, are of this form. They can be computed from the actual explicit Legendre polynomials in this way. Okay, and so what do I get here? So first of all, you might say, wait a second, you wrote your solution, right? You wrote your solution as this thing where m summed over negative l's, right? Here the m was always positive, m summed over negative l's. Well, does it actually even make sense to define this thing for negative m? It actually does, okay, or you can make it make sense. And the way that you can do this is quick aside, so quick note, we can define P LMX for negative m in the following way. So P L minus mx can be defined to be minus 1 to the m times L minus m factorial over L plus m factorial P Lmx. So this respects all of the formulas for this thing that I care about, which are namely the following. So these associated Legendre polynomials are also orthogonal. How so? The integral from -1 to 1 of P Lm P Lm prime dx is equal to 0 if m is different from m prime. And the integral from -1 to 1 of P sub Lm P sub L prime m dx is 0 if L is not equal to L prime. But we can't vary both, okay? So we don't get these if we vary both. So we don't get 0 if we vary both L and M. But if we vary one at a time here, we have orthogonality properties. Also, this length formula you get from pairing these things together with L and M agreeing, P Lm squared, right, dx. What is this? It turns out the coefficient you get resulting from this is 2 times L plus M factorial over 2L plus 1 times L minus M factorial. And so a term like this would show up in the expansions for the coefficients if you're using these as your eigenfunctions, right? And so I'm not going to say anything more about this, but these also span reasonable functions, okay? And so now comes the time for why I wrote my original separated solution first in a form where I didn't fully separate the variables. So going all the way back here to my original separation of variables step, why did I write the thing like this? Because it turns out that this piece of my separated solution is its own important thing. If we view these as eigenfunctions, right, y sub L m here in this way, we can define these in terms of these associated Legendre polynomials, and these things in their own right are a nice an example of very nice eigenfunctions called spherical harmonics. So let's recall what those things even would be in my separated solution. So my separated solution looks like this. And so what are these spherical harmonics? They're going to be like a constant times this piece, the theta and phi piece of the separated solution. And so define y L m of phi theta to be CLM e to the im theta PLM cosine phi, where CLM are chosen to make this an orthonormal set, or an orthonormal family of functions. Right, so we want them to be pairwise orthogonal, and they are by the orthogonality relations on these associated Legendre functions. and they're orthonormal in the sense that if we pair each with itself, its length is 1. So we need to choose these constants CLM to be the square root of 2L plus 1 over 4 pi times L minus m factorial over L plus m factorial. This can be derived from all of those previous formulas. These y, so these y sub L m's defined for positive integers L, L, and m, which is defined for minus L running to positive L, right? Minus L to 0 to positive L, right? So it's running from minus L to L, are called spherical harmonics. And arise all over the place in science and engineering in general. Now, the most important thing to say about them for us is that I have all of the nice basis properties here, orthogonality, and the fact that these form a basis for reasonable functions involving these quantities. So on S2, for instance, so these for us, these are eigenfunctions forming an orthonormal basis for reasonable functions defined on the 2-sphere i.e. the boundary of the 3D ball. So these sorts of things are going to show up in my solution to, say, the diffusion equation or the wave equation in a 3D ball. So these show up in my solutions to diffusion and wave equation in 3D ball. For instance, it's just an example. So these are the eigenfunctions showing up, and they satisfy a lot of nice properties. I'm not going to run through all of them here, but for us, the nice properties that matter are the fact that these play the role of the important eigenfunctions showing up, like I said, in the 3-dimensional case. So if you wanted to continue this process of separation of variables to see what you get in the 3-dimensional case, or the 3D case of the ball specifically for the wave equation or diffusion equation, these are going to pop up in some form. Okay, and so that sort of finishes all of the material that I wanted to talk about ending separation of variables. And so with the last few minutes remaining, I kind of wanted to go over very briefly a question of where do you go from here. So we've studied, at the very beginning, we used method of characteristics to study first order PDEs, right? And we were really lucky in that case that we were even able to do this for fully nonlinear PDEs, right? You wrote out some solutions to fully nonlinear first order PDEs, so that's great. When we got to the second order case, of course, we had to massively pull back and say, whoa, we can't be talking about nonlinear second order equations right now. That's a little bit too much. So we restricted ourselves instead to three very specific equations, right? The wave equation, the diffusion equation, and Laplace's equation. Okay. And so that's what we've been doing ever since, right? And eventually, after studying kind of the general properties of those equations going forward, right, first, then we returned to them with separation of variables and actually wrote out explicit solutions in terms of these infinite series, right? Fourier series analysis was very important for us in writing all of that stuff, right? So that's kind of been our trajectory. And so now the question is where do I go from here, right? So what do we do now? Like once we've done that, what do we do? So maybe I'll write that question out here. So what do we do from here? So question, what do we do from here? Let's not, go off the deep end immediately, start talking about nonlinear second order PDEs. Let's say that, i.e., what if I want to study linear second order PDEs other than the big three? Right, so other than the wave equation, diffusion equation, or Laplace's equation. The answer is that there is a classification scheme for such PDEs that relate them to each of the big three. What do I mean by that? What I mean by that, maybe I should put an exclamation mark here because that might seem a little amazing, right? That basically for any second order linear PDE you write out, it is either going to behave something like Laplace's equation, something like the wave equation, or something like the heat equation. Those are basically the three options. There's like a trichotomy here on what these second order linear PDEs can behave like, and they fall into one of those three categories, right? And so you might recall, so first of all, how does this work? And so how does this work? Maybe I'll write this as a question instead of under answer. Well, so the answer is first recall conic sections. So what are conic sections, right? They are cross sections of a double cone, right? So you think of a double cone drawn like this, and you think of a plane cutting through this double cone at some angle and some configuration, and consider the cross sections, right? The curves that result from that intersection. So there are what are called the degenerate cases. If you have a plane cutting through horizontally right at this stupid singularity like apex point, then you just get a point. So technically a point is a conic section, but we don't care about that. If you have a plane that is exactly like tangent to the double cone in this way, you get a line. So technically a line can be regarded as a conic section in that sense, but also we're not that interested. We consider that a degenerate case. So then what are we the most interested in? We're interested in planes cutting through horizontally at some height of the double cone that's not at this apex point. What happens when it cuts through like that? Well, I get circles when it cuts through like that. That is, if these are circular cones, right? I would get circles. If I were to, of course, if I were to have cones maybe that weren't exactly circles, then what would I get here? I would get like some kind of ellipse, right? I would get some kind of ellipse if I were to say, cut through the cone, even if it's a circular cone, if I were to cut through the cone at an angle here, but it's entirely, say, transverse to this upper cone here, if I were to cut through at an angle, I would get an ellipse, right? I would get something like this. So an ellipse is obtained in that way. If I had one cutting through at an angle here that doesn't come out the other side, that maybe is cutting through like this, maybe I should just show you a picture of this so that I'm not having to use my hand that you can't see through. Cutting through like this, I get a parabola, and if I have a plane cutting through exactly vertically, I get a hyperbola because it intersects both the double cones in a disjoint way. Maybe I'll just show you, like I said, the picture to remind you of how this goes so that I'm not using my hand that you can't see through. So let's do that. Let me remind you in picture if the picture is clear, right? So here's the case of getting a parabola. Here's the case of getting ellipses. And here's the case of getting hyperbolas. Okay. Okay, and of course you may remember this from Calc 2. It's okay if you don't. It might have been a while. But we can write conic sections in the following form. So in terms of rectangular coordinates, we can write any conic section obtained like this as ax squared plus bxy plus c y squared plus dx plus ey plus f is equal to 0. So we can write any conic section in this form where a and f are some real numbers, not all 0. Okay, so after we toss out the lines, we're in one of these cases that I showed you. We're either getting ellipses, we're getting hyperbolas, or parabolas. To determine what we're getting, we can define what's called the discriminant. And the discriminant is b squared minus 4ac. And this discriminant being positive, negative, or 0 allows us to determine what shape we have. In fact, there are 3 cases. Once we've tossed out, as I said, the degenerate cases of like lines and points, there are 3 cases. So case 1, if b squared minus 4ac is less than 0, we have an ellipse. Two, if b squared minus 4ac is equal to 0, we have a parabola. And lastly, if b squared minus 4ac is greater than 0, we have a hyperbola. Okay, notice that the D, E, and F, these lower order terms, actually don't factor into this at all, right? So the B, A, and C all come from these second order terms, right? Okay. What does this mean for our classification for linear second order PDEs, right? So now a general linear second order PDE can be written as the following. So let's do it in 2 variables, right? So let's do it in 2 variables just so that we don't have to write this 2 more. So let's just do it in 2 variables. Again, notice I'm going to do this for 2 independent variables, x and y. I'm not saying whether or not these are time or space variables, right? So I'm not making a distinction. So I just have 2 variables, x and y. They're just 2 independent variables. One of them may be t, right? One of them may be a time variable, but I'm just writing this as x and y, right? You can worry about that later. So I have coefficient function axy times uxx plus bxy, so these are variable coefficients, bxy times uxy, or u sub xy, plus c of xy times u sub yy, plus d of xy times u sub x, plus e of xy times u sub y, plus f of xy times u is equal to 0. Right? So this is a homogeneous, so it doesn't have a source term here, linear second order PDE in two variables. These are independent variables x and y. As I said, I'm not saying whether or not one of them is a time variable. They can be written in this form. Okay. Now, if these are constant coefficients, right? So if we have constant coefficients, this would be more simply a u sub xx plus b u sub xy plus c u sub yy plus d u sub x plus e u sub y plus f u is equal to 0, where not all a, b, and c are 0. So at least one of them is non-zero, so that this is actually a second order equation. Okay. Well, of course, this superficially at least looks a lot like our conic sections equation, right? Where instead of having the algebraic equation x squared here, now it's a differential. It's instead of x squared, it's the second x partial, right? Here, instead of being the mixed term xy, it's the mixed partial terms. So superficially, those look very similar. Well, it turns out that if we make the same categorization, so definition, if b squared minus 4ac is less than 0, we call this PDE elliptic. Because in the corresponding conic section equation, this is what we got. We got an ellipse, right, when the discriminant was less than 0. Secondly, if b squared minus 4ac is equal to 0, we call this PDE parabolic. And lastly, if b squared minus 4ac is greater than 0, we call this PDE hyperbolic. And so, notice again, this discriminant thing doesn't involve the lower order coefficients d, e, f at all. So let's look at an example, or a bunch of examples. So one, let's look at Laplace's equation. Well, Laplace's equation is uxx plus uyy equals 0. So we have a equals 1, b equals 0, c equals 1, and the rest d, e, f are equal to 0. But again, that doesn't matter for this discriminant. So the discriminant is what? The discriminant is b squared minus 4ac is 0 minus 4 times 1 times 1. This is minus 4. That's negative. So this is elliptic. So Laplace's equation is an elliptic PDE. 2. What about the heat equation? Let's do this for just, how can we think of the heat equation? This would be u sub y, we'll say, you could say, why isn't this u sub x? It actually doesn't matter. We'll call this u sub y minus u sub xx is equal to 0. Here, y would be the time variable. Okay, so this is the heat equation. So then A is equal to minus 1, right? B is equal to 0, and C is equal to 0. And so B squared minus 4AC, right, is actually 0. So this is parabolic. The heat equation is parabolic. Let's do the last of the big three, the wave equation. Again, we'll use y as our time derivative, so u sub yy minus u sub xx is equal to 0. That's the wave equation. Right here, a is minus 1. Right, recall, a is the coefficient on u sub xx. B is, again, 0, right? No mixed partial term. And C is 1. So B squared minus 4AC is 0. Minus 4 times minus 1 times 1. So this is 4, which is positive. So the wave equation is hyperbolic. Okay. Now the question, what is the point of this? The answer is that this classification scheme actually goes far enough to let us say that these types of linear constant coefficient second order PDEs all behave in a way similar to the case they lie in, right? So for instance, you could view the big three as canonical examples of each case. So Laplace's equation is a canonical example of an elliptic equation. The heat equation is a canonical example of a parabolic equation, and the wave equation is a canonical example of a hyperbolic equation. And so ultimately, the statements we want to make are like all elliptic PDEs behave similarly to Laplace's equation. So what does that mean? Like solutions to them might satisfy mean value properties, right? Maybe maximum principles. Maybe this, like this Dirichlet principle, right? This energy minimizing thing. So similarly, if I talk about the heat equation, right? So all parabolic PDEs in this way behave similarly to the heat equation. So maybe maximum principles, right? Maybe the way that the decay works, right? So all of the types of properties that the solution had, you can ask what are the similar properties that the solution to some parabolic second order PDE satisfies. And then lastly, all hyperbolic PDEs behave similarly to the wave equation. So things like finite propagation speed, the general way that we had all of these types of formulas like Kirchhoff's formula, and the resulting properties that we got from that. All of those things you can ask whether or not that's true for hyperbolic or for a solution to hyperbolic PDE, and you can see the similarity between the behavior for these hyperbolic PDEs and wave equations. So this is kind of the most obvious, immediate next step in terms of generalization. It's we spent a good chunk of our energy, right, maybe like 2/3 of the course, studying the big three. So then it's really, really nice that these big three are somehow the canonical examples for the behavior of entire classes of PDEs, right? So that's really the point here, okay? Anyway, that is all of the course content. That is it. That does it. And so hope you enjoyed the course. Let me know if you have any questions, and I will see you all soon. I'll have all of your grades input and done, within like a day of you turning in your final exams, and then that will be that. But like I said, let me know if you have any questions about anything. I'll be on email, or if you just have general questions after the course about PDE stuff, or where to go from here, recommendations on what things to look at, just let me know. Okay. Anyway, I will see you all later.